Hey everybody, Mr. Vessel here today, and I'd like to take a few minutes and look at the 2019 number 3 from the AP Stats exam, free response question. And this has a bigger theme of probability and reading a table, doing some conditional probabilities, and even checking for independence. And then there's a follow-up here with binomial probabilities. So what we'll do is we'll look through some of this, and hopefully this will help get a better understanding of some probability questions on a typical AP exam. So, first thing we'll notice, we get this description of a medical researcher surveyed a large group of men and women about whether they take medicine as prescribed, and the responses were categorized as never, sometimes, or always, and then we get the relative frequency of each category in this table below. So we got these 6 different possible outcomes basically, and we even get the totals. It's kind of nice when the totals are provided as well. And then first part here is just several different probability questions. It says one person is selected at random, and the first part is what is the probability that a person selected will be someone whose response is never, and the keyword obviously, and who's a woman. And here you can't just write down a number. You always want to make sure that you're describing what you're getting here. And one thing about this particular table, I'm going to relabel some of these actually, just to use N, S, A, M, and W, just to keep it a little bit shorter. But what we're asked to find first is a intersection basically. We want to find the probability of a person whose response was never, and they're a woman. So in this particular case, basically we can read it right from the chart. It's just this box right here. These are the percent of people, 0, relative frequencies, who are women, and never was their response for taking medicine as prescribed. So simple enough, but one of the reasons that this question can be tricky is just being really careful. This one word makes a huge difference, and part B, or not part B, sorry, the second part of part A really does that, an example of that. So what is the probability that a person be someone whose response is never or is a woman? And yeah, one word makes a massive difference in the calculation here. So, oops. So we're going to do a union in this case, and there's a couple of ways that you could calculate this value. Either way works fine. Some students like to just take there's one way to look at it. Got these 4 boxes that will qualify as a success here. So anyone who replies never or is a woman. So we got this 0, 5, 6, 4. These are the men who say never. Women who say never here, women who say sometimes, women who say always. So you could just sum up these 4 boxes. That would work really well. I'm going to go about it just slightly different. I'm just going to use the totals here. So I know that there's 53% who are women and 12% who are never. So I'm going to do the probability that someone never chooses, the probability, or never takes medicine, the probability of a woman, and we'll subtract out the probability of the intersection. Can't double count. That's 60636 from before. So this calculation is 0.12 plus 0.53 minus 0636, and you can type that in, and you'll find that the probability of someone who never takes their medicine and or could be a woman is 0.5864. And then the final, again, kind of the same theme, but one more word changes everything here. So what is the probability that a person selects to be someone whose response is never, given that the person was a woman? So this one's quite a bit different in terms of what they're asking us to get here. We're trying to find the probability that they select never, given we already know that the person is a woman. So we're reducing our subspace here. We're only going to work with the women in this case, and I like to start with that first. So there are 53% women. So the 0.53 is just what this thing is out of. It's the denominator in this case. And in the numerator, That's the probability that someone's in both of these things. That, in one calculation we just did, but the strategy that I sometimes like to suggest is you're really given this row. Out of this row, what's the probability that someone selects never? So we know that this is what the whole sample space has been reduced to now. It's our subspace, just the women, and 0, 6, 3, 6 of those respond with never. So we use the 0, 6, 3, 6 out of the total probability of a person being a woman, and in this particular case, just divide that out. And that number is 12%. So again, the big theme here is just one word can make a massive difference in the calculation with probability questions. So we just got to be careful about how we read it, and we can answer the question accurately. For the second part, for the people surveyed, are the events of a person being who responds never and being a woman independent. So this is where you get a couple of choices. I'm going to use some of the responses that we had up there from part A. But when you check for independence, basically what you want to do is just see if one of these events has an impact on the other one occurring. So we've done a lot of this work already, actually. I'm going to choose, since we already have the probability of never given a woman is 12%, I'm going to contrast that. Well, what's just the probability of never overall? So one way to check for independence, we can find this probability of someone just never taking their medication. That number is 12%. And that's given right in the chart up here. And then what we also found was that the probability of never taking your medicine just out of the women, also 12%. So what that tells us is that basically the condition of being in the group of women, it doesn't change the probability that you never take your medication. And this means that since these two probabilities are equal, these two events are independent. I'm going to be a little more specific in what we're doing. Responding never and being a woman are independent. And what's important here is that we use calculations to justify our response. So what we want to make sure is that these two calculations, they're equal. This shows that these two events are independent from each other. And then the final part, well, maybe before that final part, it also would have been perfectly fine to do this check as well. Probability of being a woman and probability of being a woman given that they never take their medication. And what you'd find is these two proportions are also going to be equal to each other. This wouldn't change the results. And a real quick check here, we know this number is 53%. And we also can check this probability. If we just check out of the never group, there's 12%, how many are women, and that's 0, 6, 3, 6. This number is also 53%. And you don't need to do both of these when you do an AP Stats question. One of the two is definitely sufficient, and they will never, if they're both equal here, they're going to be equal here as well. So in this case, either one of these are fine. Both are definitely a little excessive. That brings us to the last part. And with part C, we get this large population, the probability that a person always take medicine as prescribed is 54%. And that's also in this, up in the chart here too. If 5 people are selected at random, what is the probability that at least 4 of the people selected will always take medicine as prescribed? And in this case, if you had an infinite amount of time, you wouldn't need to use a binomial calculation here. You could make a tree diagram. You could sort of, it'd take a few minutes, so that's the problem with this method. You could say, well, they always take their medicine, that's 54%. That must mean that if they don't always take their medicine, it must be 46%. And this could represent your first person selected. Then you'd have to keep going. Maybe you could even use little subscripts, 1, 1. The second person either is going to be taking their medication or not taking their medication. And while this works, it's extremely time consuming, and in a typical AP exam setting, you probably want to be done with this question in about 10 to 15 minutes. So this method down here really isn't going to work very well for this particular question. So what's important to recognize here is that you do have a binomial situation, and the reason that it's binomial, for a couple of reasons. You've got a fixed number of trials. In this case, there are 5 people selected, so the fixed n is 5 in this case. You also have 2 options. We're going to be able to say that either they always take their medicine or not always. And then the third thing is that these 2 events, these 2 options, they're independent. These 2 options, they're independent. And I'm even going to throw this part in here because this is important too. And the probability of success is 0.54 all the time. So we can piece this together, and get a piece of paper here. So if we want to do part C on its own, we do have the binomial facet here, and if we want to find the probability of at least 4 of 5, what we're going to have to do here is we're going to have to find the probability of exactly 4 and add it to the probability of exactly 5 who always take their medicine. So the binomial calculation here, we need to start with our number of objects. In this case, there's 5 objects that we're starting with. In this case, objects are people. And we need to choose any 4 of them to be success here. So it doesn't matter which of these 4 of the 5 people are going to be taking their medication, but at least, or exactly 4 of them. So 5C4, or you can use another notation for that. You might have seen this before too. The 5C4 is a little preferred from my perspective, just because in your calculator this is typically the notation that you'll see. So 5C4 represents the number of objects, and you can choose any 4 of them to be success. And this number happens to be 5 in this case if you were to type it in. Then we also need to calculate the probability of success. So in this case, 54% was the probability that a single person takes their medication, always. And that's going to be to the 4th power. So you have 4 people that have success here. And we also have the 1 person, 46%, who will not take their medication always as prescribed. So this part on its own represents the probability of exactly 4 people taking their medication out of the 5. And then the last one, we also have to do 5. So similar logic, 5C5, 5 people, everyone in that group will take their medication as prescribed. 54% to the 5th power, and 46% to the 0th power. Then we can type all of this in. I've already typed it in. It's 1956. 0.1956 is the probability. It's to the 4th decimal anyway, to exactly 4 people. And then this one was 0.459 for the probability that exactly 5 people out of the 5 all take their medication as prescribed. Again, this is definitely possible to do with this tree diagram. This would just take a much, much longer amount of time. You'd need to go through and look at all the different branches that had 4 different A's in it. And there'd be 5 of those branches, and they would all have the same probability of occurring. They would be the probability of 0.54 to the 4th times 0.46 to the 1st. And this 5C4 takes care of the number of branches that are in this tree diagram. So this is a shortcut to calculating the number of branches in the tree diagram, and then you have the probability of one of these particular sequences. And we can total these together now. So the overall probability 2415. So the response there, almost 25% of the time, would you get at least 4 out of 5 people who always take their medication. So that was the 2019 number 3. It's got a lot of different probability tasks in it. So thank you for checking out this particular video. And if you'd like to see some more, feel free to check out some more videos or subscribe to the channel. Thanks.